Michael is a recent PhD graduate from ANU, originally from Israel. He's already made quite a name for himself, identifying gaps in our understanding of magmatic ore deposits and designing and pulling off experiments to fill them. We haven't had that many experimental petrologists on ODH yet, but this kind of work really underpins our interpretation of natural systems, and as Michael will show, it can have direct and profound implications for the sort of good old geological mapping and hand-lens approach to mineral exploration. So Michael, the next 20 minutes or so are yours. I'm really looking forward to what you have to say.
Yeah, thank you. Thank you. You're giving me a bit too much credit. I did some experiments and I explain what I found in them. Anyway, yes, so let's start. Thank you for inviting me. It's a great pleasure to be here, especially at 6 p.m. here in Australia, where it's all nice. Yeah, so I'll talk about a recent paper that we had out, and some of you might have seen the link to it for the paper in the email. I'll show it a bit later. Those are some experiments that I did with carbonatites, and I'll talk about how that translates to what we actually see in nature in real carbonatites. Now, this is work that was done at ANU, the Australian National University, funded by the SOS REE project and in collaboration with Francis Wall of the University of Exeter. And I'll just start with a quick introduction to what carbonatites are. So carbonatites are rocks that have igneous carbonate in them, mostly calcite, also dolomite, also ankerite. Ankerite being the iron-rich variety of dolomite. We care about them because they host most of the world's light earth element deposits. Okay, we all know Belgrano, that is the best example, and I'm saying here light earth elements, and that's a very important point because people often talk about carbonatites with the hype of that it has the earth elements. No, it actually no, because 99% of the budget is cerium, lanthanum, praseodymium, and neodymium, and usually all of the other 10 or so are just 1% or even less than that. If you're lucky, then you can make a bit of dysprosium as a byproduct, but pretty much we're talking about those 4 elements in carbonatites. Now, when you look at carbonatites, this is pretty much how they look like. So here's an example from Canada. And what you're seeing here, this part here is the carbonatite. And you have calcite, or a calcite carbonatite on the outside. As you go inwards, you see the dolomite, which is a magnesium carbonatite. And inside is here, that's the ferrocarbonatite, or where we have the ankerite and the iron and all of that. These things are usually about a few hundreds of meters big or wide, and surrounding them you have phenites. So phenites are all of those other things which stretch up to several kilometers around the carbonatites, where you have sodic and potassic alterations of fluids that came from the carbonatite intrusion. It usually tells us that the magma that made a carbonatite had all of those together. So it wasn't a calcium carbonatite melt, it was a calcium, magnesium, iron, sodium, potassium, and all of that together in one liquid. The mineralization is usually inside the core, so inside the iron-rich part or the dolomite. Okay, now that's not always the case, and this is a very obvious example. You don't always have this ring structure, but you do see that even if you have a partial exposure or instead of a ring structure, you have dikes, usually the mineralization is in the magnesium and the iron-rich parts of the carbonatite. For example, in a Burbankite, it's hosted in the dolomite. Here's a close-up. So this is a figure I stole from the SCG book 4 years ago. And here, the stuff here is monazite. And as you can see, the monazite, which is the ore, is hosted in dolomite. And and in the upper bit, there's the basnasite, which is another ore. So that's the carbonate. It's hosted in this thing here, which I guess used to be ankerite. And now it's all altered into some iron-rich hematite, something, whatever. So, and the other thing is that we see in carbonate that I was telling you about those phenites that we have around them, right? So here's a section of how a carbonatite might look like. So we have all of the core inside, which is the calcite and dolomite, and around we have all kinds of late veins, and here's a phenite. So this is alteration by fluids that came off the carbonatite. And what you often see there is that there's a heavy rare earth element enrichment. And in some extreme cases, it might even look something like this. It looks very impressive, but usually you don't have a lot of this, so it's a sub-economic, and you'd be very lucky to find phenite that you can mine for heavy, for the heavies. Still, this is something that we see and we need to think about when we're discussing the carbonatites. Okay, so in short, we have the light rare earth elements inside the carbonatite, especially in the magnesian or iron-rich carbonatite. Again, not always, because there are always examples of places like in China, in Manuping, where the mineralization is inside the calcite carbonatites, but those are usually exceptions. We have the heavies outside the main intrusion in phenites. And the other thing that we usually see is that when you look at fluid inclusions in the earth element minerals and stable isotopes and all of that, we get the indication that they formed at temperatures lower than 500 degrees, sometimes even as low as 300 or 200. And this leads to the idea that the mineralization is some kind of late hydrothermal thing. So you had the carbonatite magma at maybe 700, 800 degrees. Then something happens, which we don't really know what. Then the minerals form at 200. What happens in the 600 degrees in between? It's a good question. So I did some experiments to try and find out. So that's the paper, and it's open access. You can go and download it, and that paper has everything I will say now and even more, because I'm only limited to 20 minutes or so. The way I did it is I made a carbonatite. So we have big machines, about this big, that can go to high pressure and temperature, and you put some rocks inside them, and you melt everything, and you do stuff, and then you take them out, and you make a rock, and then you look at what you got, and what are the smart things that you can say from that. So those are the compositions of the carbonatites I put into my experiments. So it's not really based on anything. It's just an educated guess on what a parental carbonatite melt might look like. So we have calcium, magnesium, iron, phosphorus. Here potassium, here some sodium. About a weight percent total of earth elements. And instead of putting all 14 or 15, I used a lighter earth element, which is lanthanum in my case, and a heavy, which is dysprosium in my case. The reason for that, because it's much easier to analyze when you have only one and not 15 elements. I'd also tell you that the amount of dysprosium I have here is probably much more than you have in natural carbonatites. But that's the good thing about experiments. You can put anything you want, and then it's more informative than what you can get in natural systems. Of course, it's a carbonatite, so it's full of CO2 in the form of carbonate, not CO2 gas. And there's H2O and fluorine and chlorine and all of those fluxes that we think of when we're discussing carbonatites. And what I did with those, I put them in a capsule, and over 4 days or 96 hours, I took them from very hot, so 1200 or 1100, to 200 degrees, which is about as hot as your kitchen oven. And at the same time, I also decompressed them. Okay, what did we get? So I will start with this experiment, with the potassic experiment, and that's the result of the experiment. And what you're looking at here is a QuameScan map. So this is my experimental capsule after I finished the experiment. Okay, it's about 1 centimeter length or height or wide or whatever, and about half a centimeter in the thin part of it. The colors are mineral identification by automated mineralogy, so an SEM, and all of the colors, there's a legend up here, so it tells you what the things you're looking at. Now, what's happening here is that when I tell you that an experiment is, for example, at 1000 degrees, it's only at 1000 here in the center. On the edges, because of how we build the instrument, it's a bit colder. So if it's 1000 here, it might be 995 just here, which means it will start to crystallize from the outside inwards, or from the top and the bottom inwards. So things that form at the edges form at high temperatures, 1,000, 900, 800. Things that are closer to the center form at lower temperature, 400, 300, or 200. Okay, so what do we see? We see that at the very top and bottom, we have calcite. So this thing is calcite. Here's the calcite here, and a bit of apatite. So this is essentially a calciocarbonatite. That's the calcitic carbonatite, and apatite is probably the most common rock-forming minerals in those. Okay, so all good so far. Then as we cool it down even more, we get this thing, which is a bit darker. That's the dolomite, again, with some apatite inside. And it's a bit hard to see here, but at the very edges here, it gets a bit more brown or yellow. That's where it becomes more iron-rich, so more like ankerite. The interesting thing is that in these parts, there's no mineralization. This is all just apatite that doesn't have a lot of earth elements inside, calcite, which is nothing, and dolomite. So we're essentially fractionating the carbonatite magma into something that is much richer in all of the other things I had in the experiment. What are they? All of the stuff inside here. So at the edges here, there's a bit of siderite and magnesite. So that we are ferrocarbonatite. And inside, deep inside, you have those white-green thingies. This is potassium bicarbonate that was dissolved in the fluid. So this was some kind of hydrothermal fluid. I wouldn't even say it's a hydrothermal fluid. It's not in the sense that we think about of just H2O with some stuff in it. It was some kind of very brine-rich melt evolved from the carbonatite. At no point there was separation between a carbonatite magma and coexisting hydrothermal liquid. It was all just one continuous thing. So I have this, and I have some monazite. So here's a monazite in here. Here's the monazite in there, and because some more scattered down, that's where the light rare earth elements are, in a very insoluble light rare earth element enriched mineral. There's all of the red stuff. The red stuff is this quench stuff, so things that form as I cool down the experiment from 200 to room temperature, and this is full of dysprosium, so the heavy rare earth elements. So what happens here? I'm crystallizing carbonatite, I'm making barren calcium carbonatite and dolomite carbonatite. Then at the very last stage where I have the iron-rich part, that's where the siderite, I'm also forming monazite, light rare earth element minerals. Heavy rare earth element minerals are still in solution, they're still mobile. This is an experiment, this is a closed, capsule closed system. Fluids have nowhere to go, but in a natural system, all of this will just go outside. And when you have a very potassium-rich fluid going outside to the wall rocks, you will make a phenite, because a phenite is, it's an altered rock made of, phlogopite, caspar, all of those potassic and also sodic minerals. Together with them, we will have the heavy rare earth elements. Now, that's one of the reasons, not the only one, but one of the reasons why we don't have heavy rare earth elements in carbonatites, because they just go somewhere. So if we take this and superimpose our natural carbonatite, so in here we have a calcite, there's the calcite, inside we have the dolomite, so here's some dolomite, and inside we have the ferrocarbonatite with the ankerite and siderite, and that's where the mineralization is. So when we see that in nature, it's not an accident. This is what thermodynamics tells us that will happen. So this is something that we can count on when we're exploring for minerals, because if we have a calcite carbonatite, then we know that there's a ferrocarbonatite nearby. Maybe we don't have to drill into the calcite one because there will be nothing there, and save us some money on the way. Let's look what happens when we're doing the experiment with sodium. Now, this is a bit more complicated, but I'll guide you through it. So in the beginning, we have our calcite and apatite. So the calcite carbonatite here and here on the edge. Dolomite just here, and here it's easier to see how it's becoming ankerite. It's a bit more yellow around the edge here and also there. And of course, we have the magnesite and siderite as before. In here, we have, again, a very solute-rich brine melt hybrid thingy, which isn't really a carbonatite melt. It's not really hydrothermal fluid. It's something that I'd like to call a brine melt. The hole here is just from the drill when I drilled into the capsule. So this stuff here used to be all of the other things. And of course, we have sodium bicarbonate, again, just like we had before with the potassium bicarbonate. Now, here we don't have any monazite anymore. Instead, we have all of those bizarre minerals. So there's borasquite, atelite, pruveliite, bonstedtite, things I've never heard about until I made them. And they're very interesting because those are pretty much sodium carbonates, sodium phosphates, sodium fluorides with some stuff in them. Now in here it says magnesium, iron, calcium, not too interesting, but you have it in the paper. All of them also host some rare earth elements in solid solution, okay? The interesting thing is that we have this, the monazite and the burbankite. So those are burbankite group minerals. So very sodium rich carbonates with rare earth elements in them. So here's one here, that's the dark blue one. And there's another one over here and another one over here. Those are where the light rare earth elements are in there. And the heavies, again, they're in the quench. So they will be in a mobile phase. And when this intrudes into a real rock, this will go outside and make a phenite. This time it will be a phenite with sodium. So things like agerine, phetsonite, albite, all of those. Okay. Now, this burbankite is forming at relatively high temperature. So this is the first thing that's forming after the dolomite and ankerite. I don't exactly know at what temperature, but I'm guessing based on what we expect from the stability range of ankerite, that it would be at around 600, maybe 500 degrees. Those things are not stable. It is essentially sodium carbonate. So when you take that and you have a later fluid going through it, you dissolve it away. You dissolve all of those things away. All of those minerals are soluble. You just need a very weak acid or a fluid with sodium, and they're gone. Leaving behind rare earth elements, which are insoluble in non-acidic systems, and this is a non-acidic system because it's full of calcite. And leaving behind, so rare earth elements, fluorine, calcium, all of the things that end up in the mineral assemblage that we usually see when we look in carbonatites, because the mineralization itself in carbonatites would be bastnasite, parisite, zincosite, ancilite, so monazite, all of that. Those minerals are not the primary mineralization. They're just replacing those minerals that we've never heard of before because they're simply not stable. And they're replacing them in situ, so they don't move. They form in one place and they stay there. And all of the later alteration, with fluid inclusions and temperatures that go from 200 to 500, and stable isotopes, all of this is just confusing us and making us miss the actual mineralization, okay? So a summary so far would be something like, okay, we have the light earth elements in the magnesium and iron rich carbonatite. If we have a potassic one, we'll have monazite. If you have a sodic one, we'll have burbankite. If you have a mix, which is most likely what you have in natural rocks, because you have a bit of sodium, a bit of potassium, you might have both. You lose the burbankites. And there were quite a lot of papers recently saying, oh, look, this thing here, I think it was a burbankite, but I'm not so sure. So now I'm telling you, based on my experiments and the thermodynamics, that there's a very good chance that this used to be a burbankite. And the important thing here that it means the earth elements are not soluble. The burbankite is, because the sodium goes away, not earth elements, so they stay where they form. With regards to heavies, they just go out into a phenite, and that's a good exploration thing to keep in mind, because if you see a phenite, a large, extensive phenite, and you do see all kinds of veins with unexpected or unexplained mineralizations of heavy earth element minerals, like the one I showed you earlier, then this is a good indicator that somewhere in the carbonatite, there was a burbankite. So there was this process that concentrated earth elements into one very volumetrically limited area, and this is something that you want to target for exploration. Okay. Now, with I showed you the experiments with sodium and potassium. What happens if we don't have sodium and potassium? So here's another experiment, and this is a bit harder to understand because of all kinds of reasons that I explain in the paper. But what I want you to see is that we don't have monazite, we don't have Burbankite because there's no sodium, but all of those blue things here, those are bastnacites. Okay, so it is possible to make bastnacite directly from the carbonatite. Do pay attention that it's always in cavities and bugs and cracks and holes. So it's never inside the calcite. It's never inside the dolomite. It's always in these very late stage parts of the carbonatite. But it's very unlikely for a natural carbonatite to have no sodium and no potassium. It is possible, however, for a carbonatite to be contaminated with silica, okay? And I'll just show you this thing. This is a figure from the paper. And what happens when you do have silica contamination into your carbonatite, you will start making minerals like, look here, like phlogopite and edgerine, which will sequester all of the sodium and potassium and will not allow formation of something like Burbankite, okay? So this will actually keep the light earth elements in the carbonatite. I think that this is what happened in Anenburg, I'm not sure. But really the holy grail, the big thing that we want to look for is this, when you have sodium and potassium. So you have a very large phenite that is easy to find. You find some kind of heavies in there, then it tells you, yeah, the carbonatite next to it probably had at some point Burbankite, and this is the thing that you want to target. Again, I think the main take-home point here is that all of the late fluids, things happening at 300 or 400, they don't do much. They only confuse you. They just reshuffle rare earth elements in situ from one mineral to another. At no point I have seen exsolution of solute-rich fluids from the carbonatite, and I honestly think this is not something that happens in carbonatites, unless I'm proving wrong, and I'm happy to hear people's opinions. And I think that's about it. I think that's the last slide. So yeah, it was. So
excellent. Keep screen sharing there, Michael. Yeah, and then afterwards, Neila, you can just grab the screen share. That was fantastic, Michael.
How did I go with time?
Very well. Yeah.
Okay,
on mark, really well illustrated, and yeah, I mean, it's the reason I invited you on. It starts from this
thank you,
little experiment and becomes this very simple to understand exploration story. So, Kathryn, if you'd like to have a chat with Michael, we'll listen in.
Thanks, Tom, and thanks, Michael. That was really good. Really good kind of summary of the paper, and I think this work is so important because we see some of these features in natural carbonatites, but by doing the experiments, you've been able to kind of quantify how those fit together in the real world, which is such an important thing to help us understand how to compare different carbonatites. I've got a few questions, of course.
Look, I'll say something, and there's one big limitation in my study, in our study. There's no sulfate. And for those of you who have been following the carbonatite literature in the past 2 or 3 years, sulfate is the new trendy thing that makes rare elements move. Maybe.
My first question, Michael. The first question I've got written down here is, did you think about including sulfur in the starting compositions?
Exactly. So, look, I'll give you the answer. Yes, I have, but that would mean that I'd have to change the experimental setup, and then it makes it harder to compare experiment to experiment. Yes, it would be amazing if I would have an E here, another experiment where it has sulfate. But look, the problem with sulfate, and again, I don't know because I didn't do the experiment. So what I'm telling you now is based on what my personal opinion is, which may be very well wrong. But I think that the problem with sulfate is that, it's always there. I mean, well, it's most of the time there. I mean, you see it in fluid inclusion, you see it in all kinds of things, but was it the important thing for the mobility of the earth elements? And when you look at fluid inclusions or melting inclusions, there's always sulfate and sodium, sulfate and potassium, right? And then the question, is it actually the sulfate doing stuff, or is it the sodium and potassium? Because if you just take calcium sulfate, well, calcium sulfate is anhydrite, which is not it's a bit soluble, but not too much. And it's like the thing with chloride. If you take lanthanum chloride powder and put it into a beaker of water, it will dissolve. Same thing with lanthanum sulfate. It is a soluble chemical.
Mm-hmm.
But you always have the limiting factor, which is phosphate and fluoride. So those are the things that will deposit. So if you have apatite, for example, or britholite, so rich apatite, it doesn't matter how much sulfate or chloride or carbonate you add, you will always have that apatite. So we always have to think about what's the least soluble phase in the system. Okay. But again, I don't know because I haven't done the experiments. It's on my to-do list, but it's not at the top of my to-do list, and I apologize. And if someone wants to come and do a PhD at ANU, you're more than welcome to go and do that and run those experiments.
It's a brilliant answer to that one. Good, thank you, Michael. So the thing that I'm really interested in, I guess, is the potassium versus sodium and what controls that. But I suppose my first question is, you started out with, I think, almost the concept that you have quite balanced amounts of rare earths and carbonatites, and that then you showed that the heavy rare earths are often lost into phenites. But if you look at some recent work by people like, say, Zineb Nabil, a lot of carbonatites may well be formed by immiscibility from alkaline silicate melts, and they may already be preferentially enriched in light rare earths during that process. I mean, what do you think about that in terms of the initial compositions?
I will show you something. Okay, yes. Mm-hmm. Yes, you are correct. And the thing is that I have more experiments that, I haven't found the time yet to fully analyze and write a paper, but there are many factors starting from generation in the mantle up to the upper crust that will favor light rare elements to stain the carbonatite. And yes, a carbonatite, even when it's deep and haven't fractionated yet, so when it's still at 800 or 900 degrees, will be very much enriched in light rare elements relative to heavies. Okay, and just the gray stuff in the back here. We're talking about 10,000 versus it goes to like 10 here, so 1,000 times more. So the thing with the potassium and sodium, they take something that has very little heavies and takes even that tiny amount out, okay? Which is why it's sub-economic. I mean, you never had lots of heavies to begin with, you just take that a tiny amount and you take it outside. So it's useful as an exploration indicator. Whether it's something that really affects the light earth element budget of the system, probably not. Yeah, that's I think pretty much it. Like you had a bit, and then even that bit you take out of the system.
Yeah, fair enough. And in terms of then potassium and sodium, obviously you got quite different results in your experiment, and we can fit both of them with kind of natural settings, if you like. With the potassium, you saw the heavy rare earths being lost in the fluids, but the light rare earths being locked up in monazite, which is good, of course. Monazite is a very useful mineral in terms of economic rare earth deposits. Whereas in the sodium-rich compositions, you saw what we see in many carbonatites, which is that you form these initial minerals that then get dissolved and replaced by things like bastnäsite, another very useful mineral economically. But what do you think in natural settings controls that difference between potassium-rich and sodium-rich?
I have no idea. It could be something at source. If it's a direct mantle melting or immiscibility, at what stage did the immiscibility happen? What types of continental crust did it go through, because a carbonatite will always react with the rocks around it. So maybe in some chemistries you can leach away sodium, in others you can leach away potassium. This could be, there could be pressure effect. I don't know. This is what we know from this paper, by the way, from the polyelite paper, that, with deeper fenites, the sodium, with shallower ones, we have the potassium. I don't know. Look, I'm only an experimentalist who puts powders into capsules in the lab. I'm giving you this information now, so you guys can go to the field and see if it makes any sense. And I would also remind that, look, I only did 4 experiments, and I only did 1 experiment with sodium, 1 experiment with potassium. So this is showing you general trends, okay? Like what things can happen and where things are aspiring to, but trying to pinpoint exactly what controls the sodium and I did not do an experiment where I have both sodium and potassium. Maybe I should have, right? But no, there's only one me and so many experiments to do. So I'm limited in that sense.
Luckily, we do have some thoughts on this because of the more ultrapotassic things being more closely associated after subduction. And that's what you tend to see in the alkaline magmas. So it'd be really interesting to see if you can also link the carbonatites associated with those more potassic silicate magmas, if those are showing symbols, the signs of your more potassic mineral assemblages, which I think on a totally qualitative basis, I think they probably are. But yeah, we're working on writing some of that up at the moment. So we'll be citing you, Michael, I promise.
Yeah, thank you. Look, there's also, next year, there will be an elements issue out on carbonatites. And in there will be a bunch of papers on all aspects of carbonatites, but some of our thinking, or my thinking, will be in the ore deposits paper. And the thinking there is even more evolved than that paper, right? Because this was submitted in March or something this year. And in the 6 months since, I have thought about more things, which are not necessarily in the paper. Yeah, look, it's we are learning more things about carbonatites every day, and I was fortunate enough to review some papers on carbonatites in the recent months, and they're great ideas, and it's pretty much changing what we think and know on what can happen, what cannot happen in carbonatites, which I think is the more important thing. Like, because the thing with carbonatites is people always go and study them after they did work on silicate rock. So this thinking that you have in your mind when you're working on silicates, then you apply it for carbonatites, and that's wrong because those are completely different chemical systems. Yeah, so it will be fun in the next year or so in terms of papers coming out, I guess.
And on that note, that's brilliant. Thank you, Michael. I'm going to hand over to Tom because I see he's got some other questions for you coming up.
Yeah, so do you want me to stop my share or not yet?
Sorry, you dropped out for a second for me there, but we have a set of really interesting questions in the chat, and we have about 5 minutes or so to ask them. So Thomas Krumer, you have an interesting one there. Would you like to ask that yourself? You can unmute yourself when you're ready, or I can ask it for you.
Yeah, can you hear me?
Yes.
Yeah, I can hear you.
Right, okay. So I'm a layman, yeah, so but from what you are telling us, I understand that you suggest that there's a common pattern to all carbonatite deposits.
Yes. Yes. And in the paper that I told you about that we'll have in elements, one of the points that we will make is that in most cases, it doesn't really matter where the carbonatite is coming from, whether it's a direct mantlement or miscibility or all of that. It's like in silicate melts, you have the granite minimum, and it doesn't matter with what you start with, you always end up with quartz, feldspar, and albite. So rare earth elements will almost always, not always, there's never an always in geology, but almost always will be incompatible during high temperature igneous fractionation in carbonatites. light earth elements will always be deposited in one form or another, either monazite or Burbankite, which later is altered to plasmasite, inside the carbonatite itself, and heavies will go out. You can always find exceptions, but that's the basic idea that I am selling you, yes.
Great.
So that would make exploration a great deal, say, easier. If you find the one thing, you can take the other thing for granted. Is that correct?
Look, don't base your investment on me, right?
Of course not.
But look, the idea here, like, why did we even do those experiments, right? So the point is to see what are the things that are likely to happen, and then if we can base exploration on that and make it easier or cheaper to find ore deposits, then that's wonderful.
Thank
And
you.
yes, yeah.
I mean, the logical next step is to go out in nature and show that this happens again and again, I suppose, from these experimental studies.
Look, I think it happens again and again because that's what you see in papers, and like this is how it is.
I think you should maybe invite Holly Elliott to ask a question, Tom, for that bit.
Okay. Holly, you can jump the queue there if you like. You should be able to unmute yourself.
Hi, Michael. Nice to see you again.
Holly.
Hi.
Yeah.
Mine were actually more comments than questions. So as you said, I think sodium potassium would really be the most interesting next step because as you saw that the rare earths acted ever so slightly differently and went into different phases in both the potassium and the sodic side. But where we have a system that has both, it would be really interesting to see what comes out when, because we generally do see some variation in the rare earths and the rare earth minerals and the sodic versus the potassium. And also you might be able to answer the sort of time-honored question of how the sodium and potassium form and also their temporal association. Because of course the sort of traditional model has the potassium coming out after the sodium, but a lot of our most recent field observations actually has the sodic systems going through the potassic breccias. So it'd be really interesting to see that sodium potassium maybe next step if you are going in that direction.
Look, if I'm to generalize for my experiments, you do see that in the sodium experiment, I have all of those minerals here. So big, nice crystals are sodium minerals. If you go back to the potassium experiment, we don't have them. So all of the potassium ended up in the brine. So maybe it would be correct to say, and I'm not sure because I haven't done the experiment, but just guessing that sodium would be something that fractionates first, enriching potassium in the later lower temperature stage, maybe.
Yeah, that would just be really interesting to see if it does correlate with the field observations or not. But also it might be worth thinking about the iron concentration itself, because interestingly, we rarely see any rare earth mineralization associated with systems where we only have a pure calcite carbonatite. I mean, Bonobo is the obvious exception here, but it would be really interesting to see how the magnesium and the iron in relation to the calcium are different variables, because you've got a mix all in one crucible essentially at the moment, haven't you?
Yeah, it's one big soup of everything.
Yes, well, excellent talk. Thank you very much.
Thanks.
Great. Thanks, Holly. Okay, I think we can fit this one last question in from Mike DeWitt, if you want to unmute yourself.
Thanks very much. I'm also a bit of a layman when it comes to carbonatites. I'm more working in the kimberlite field. But I was interested to look at your diagram figure there, where you compared the size of the phenite zone.
So this one.
No, I think it was one of your last cartoon diagrams.
Oh, the last one. This one. Yeah.
No, it's a cartoon diagram. Yes, that's one. Yes. why is the Fernite zone so narrow in a silica saturated rock compared to one with in a zone which is silica undersaturated? I'm not quite sure if I understand that.
Well, that's because the carbonatite will leach silica from the rock, okay? And that silica will bond with the sodium and potassium to make silicate minerals. So you have aegirine, which is for example, right? It's an example. You'd have aegirine, which is a sodium pyroxene, or you'd have phlogopite, which is a potassium mica. And then you'll have less alkali elements, or less sodium and potassium available for the late stage brine, and then you simply have just less of that to make a phenite. This is something that there was a paper by Johannes Giebel and co-authors in JPET about a year ago, which showed that in a nice way, this reaction leaching. I think you can also see it in other places, but it's a bit harder because very often people would just say they have a silico-carbonatite and assume that all of the silica was dissolved in the carbonatite, but that's not possible because the solubility of silica and carbonatite is very low. So it's leaching everything from the silica-saturated wall rock, making those silicates in the carbonatite, and then you're removing, essentially, you're fractionating away sodium and potassium.
Okay, thanks. That makes sense.
Great. Thanks so much, Michael.